Have you seen this image? Do you know the size of the dish used to view this black hole? The size of the telescope. The size of Earth. It was a huge dish with many holes. So it's one of the greatest achievements, probably. It's not really a dish. It's not like the telescope dish. But at the end of the day, it's just a huge telescope with huge holes in it. The size of the telescope is the size of Earth. You see, the black hole is not this thing over here. The black hole is estimated to be 1/3 of that dark region. So what happens actually is, if you have a black hole, you see, we have been studying circular orbits. We assume the existence of circular orbits and then solve for the circular orbits. But close to the black hole, there are no circular orbits. If you are very close to the black hole, if this is your black hole, this is the event horizon of your black hole. There is some other radius inside of which there are no stable orbits. So what this essentially means is, if the only force acting on the object is the gravitational pull of the black hole, and if that object enters this region, then it inevitably falls into the black hole, into the event horizon. Of course, if there are other forces, for example, if you push your object outwards, in that case, you can still have some object in this region. It can get out, get in, etc. But there won't be any stable orbit. Stable in the sense that if the only force acting on it is the gravitational force, it has to fall into the black hole. So what happens is the black holes are not isolated. So there are all these other materials around it, and they attract it. So one thing that might happen is, here is your black hole. And it might be a star. There might be a star nearby. And now you can think of what about the equipotential surfaces for gravitational potential? Well, if you consider the equipotential surfaces close to the black hole, all this region will be an equipotential surface, for example. This region will be an equipotential surface. And there will be this equipotential surface. So, this is the star. This is the hole, and these closed loops are the equipotential surfaces. So, very close to the point object, they will be spherical. As you go away from this circular object, they will be deformed by the presence of the other object. So, let's ask us what happens if the black hole and the star comes even closer. And then there comes a point, there comes a distance where here you have the black hole. Here is the star. And here is our equipotential surface. Well, of course, the surface of a star is actually an equipotential surface. So in that case also, the surface is an equipotential surface. So if they approach too much, then what will happen is this shape will not be circular anymore. So the shape of the star will be this much. It will be elongated. It will fill this region, fill this lobe of the equipotential surface, but then the material can leak. They can go to lower potentials through this point. So then the material will start falling. And as they are falling, well, it's highly unlikely that it will just go head-on. It will start circling the black hole. The material will leak and start circling the black hole. This is what's called an accretion disk. So it starts eating, in a sense, the star. Well, if they even approach further, this process can take a very short amount of time. But you see, as they are moving towards the black hole, this material starts moving very fast. And they also collide with each other as they are accreting the black hole. But large energy, due to collisions, it will be randomized, but that is what we call the temperature. So the temperature of this accretion disk will increase. Well, we have seen black body radiation. Anything that has a temperature emits radiation. And in fact, the temperatures are so high that they emit in the X-ray spectrum. Some of the X-ray sources are assumed to be the accretion disks of very massive dense objects. You see, the event horizon is over here. Nothing that enters there can leave. But here we are outside the event horizon. The accretion disk is outside. It gets heated up, so it emits black body radiation. So what we actually see in this image is the accretion disk of the black hole. So that image, that bright regions, is the accretion disks. So there is this accretion disk around. The black hole is somewhere inside this shadow. And as I said, it is estimated to be around 1/3 the radius. So, and as you can see, there is nothing coming out from there. And this unevenness is bright over there. It's darker on that side. It tells us that this black hole is spinning. I was trying to find a comparison of the simulations and the actual observation. I couldn't find it, but this was the prediction obtained by a simulation of a rotating black hole. It coincides exactly with this image.
Do they know about anything about the temperature?
The temperature of, well, they don't mention it. I mean, since we know the color, we know the temperature. Yes, what they say in these articles is that if the black hole is spinning, when the black hole spins, it causes the space-time itself to rotate. It drags the space-time. And the regions that are moving away from us should be dimmer than the regions that are moving towards us. Well, that is what is written. I cannot claim that I understand it.
Hocam, black hole dediğimiz şey zaten çok ders değil mi? Nasıl onun potential daha az oluyor da yüksek potential star onun içine bakıyor?
Let's look at the sizes. Just give me an estimate of the size of the radius of the sun, of the star. Well, I mean, for a typical star, give me the...
6,000 maybe it would be.
Let's say if this is 1, then the radius of the black hole will be typically 10 to the power minus 10. Let's say. I'm just making up these numbers. It's not that I know it, but the black hole is much smaller. Now, if you have let's say you have a star of mass m, you are at a distance, let's say d. If that star is converted into a black hole, but you stay at the same distance, you will not feel any change. So the potential will be the same. So it's essentially a matter of the distance. Whether the potential is larger or smaller doesn't really have any too much meaning. So here the idea is what changes in the black hole is you can approach the center without having your mass outside. That's why it's so strong. It's so strong if you are very close to it. You can get very close to it. You cannot get very close to all the mass of this sun. That's what makes black holes, quote, stronger. But they are stronger very close by. You see, if your question was about this one, it's mainly related with what is this distance, what is that distance. But what I can say is that there will be a distance between the center of the star and the black hole such that at this distance, one equipotential surface will coincide with the surface of the star, and that same equipotential surface will extend and will also contain the black hole. And here, although it's always said that it's the image of the black hole, it's actually the bright regions is the accretion disk, and the black hole is somewhere in between.
Hocam, öncesinde biliyorlar mı orada karar olduğunu yoksa?
Sure. They were, well, let's say, knowing that there is a black hole, okay, this is probably the first time that we know that there is a black hole somewhere. Before,
Samanyolu'nda var mı peki?
yes, that is the second image that we are waiting. Okay, I'm saying yes, but just take it to mean that we think that there is one. You see, the only thing we have are our theories. Our theories predicts that they should exist somewhere. And we knew that this object had all the properties of the black hole. But did we know that our theories were correct? No. But now at least we have another test of our theories.
Bunu gerçekten meçhul olduğunu nereden biliyoruz? Yani başka bir kesin olamaz mı bizim hala bilmediğimiz nasıl predict edebiliyoruz? Bu kesinlikle predict olur.
Well, let's see. Let me repeat myself. We have our theories. We don't know whether our theories are correct or not. But we have our theories based on, if you think of general relativity, well, we have observations made in the stars, not in the stars, in the sun. We have observations in the solar system, like the precession of the Mercury. We have our fundamental guiding principles, let's say. One of those things was the equivalence of the inertial and gravitational mass, and which makes predictions about distant galaxies. Now, when we looked at this galaxy, this cluster, we could measure its mass and some of its properties, let's say, and our theories predicted that this object should be one of the solutions of our theories, which we call black holes. And then when what should a black hole look like? Well, a black hole should look like more or less like this. And then we make the measurement. And our measurement also looks like what we predict. So on one hand, we have our theories which predict that we should make such measurements. On the other hand, we have such measurements. So most probably our theories are correct. Just let me underline, I am on purpose, I am avoiding to say that we know that it's a black hole. As you said, maybe nature is more weird. Something just pretends to be a black hole, but it's not. We don't know. But that is the case in everything. Even when you talk about Newton's second law, which we strongly believe that it holds, what we know is that it holds for all the measurements we did until now. Maybe next year there will be a new measurement which will violate the Newton's second law. But I wouldn't bet on that. Now, this is probably as close as we will get to know that there are black holes.
Hocam siz bu black hole'a hangi açıyla baktığınızı gösterir mi? Fotoğrafta tam olarak neresinden baktığınızı? Ya da işte bakacağınız yere göre değişir mi?
Have you watched the movie Interstellar?
Evet. Ben bunu sormuşlar. Bu etrafındaki halka gibi.
Yes, this is the image.
Neden şu şey yok mesela?
You see, here you see the accretion disk. This is the accretion disk. It's not going around like this, going like this. So you have the black hole, there is this accretion disk, but the black hole's gravity is so huge when the light from the accretion disk on the other side is trying to go up, the black hole just pulls it and it moves in that direction. So this is the black hole. You see this part of the accretion disk. When you look from here on the top, you also see the accretion disk on the behind. So this is behind the black hole, these two disks. Not at the top or at the bottom, it's behind the black hole. Now, we don't see such a line going through the black hole. So most probably, if this is the black hole, the accretion disk we see is something like this. It's a bit tilted. Why do we think it is tilted? Because of the different intensities. It's likely tilted something like this. This part seems to be moving towards us, and that part seems to be moving away from us. That is why this is lighter, this is darker. But as I said, if we were able to look at it from that side, you see this, if let's say, we were looking from here, this is the black hole. If this were the accretion disk, then we would probably see it completely symmetrical and no line in between, because the accretion disk isn't oriented like this. It is slightly tilted. Why we think so? Because it's not uniform, but it's not tilted enough so that we don't see that we don't see this image. So if the black hole is at the center, this is the accretion disk. If we were looking like this, we should see this, but most probably we are looking something like this, with a slight tilt. No, that is due to the rotation of the black hole. This region? I don't know. That I also don't know.
Sadece rotation hareketi mi yapıyorsa hangi orbiti ya da vesaire var?
Let's enjoy our discovery first. Okay. Nice black hole picture. There are all these questions that we don't, well, at least probably some people know the answer for. I don't.
That telescope area that took this photo, there are no telescopes in space that contribute to this, right?
No. And hopefully they will build some.
You said that if we know color, we can understand its temperature.
Yes.
Can we understand its temperature?
We had already discussed the black body radiation. Okay? Sufficient answer? So we should look at the spectrum of light and we can, for example, look at the wavelength at which the spectrum has a maximum, and we know that that wavelength multiplied by the temperature is a constant for every black body. So that is one way. Or you can just try to fit the general shape of the spectrum. Not just the maximum, but the general shape. Okay. Anyway, I will search for the simulation results during the break. Let's go back to our quantum physics. Or quantum mechanics now. Yes.
X'in expectation bölüsünü rahat bir şekilde aynı üzerin içerisinde probability ile çarparak falan bulabiliyorken, bir şekilde gelerek bulabiliyorken neden momentum'u kullanıyoruz?
Well, we will discuss that today. So you see, we had written down our equations. We said that if we know the wave function at a given time, then we can determine how it changes with time using the time-dependent Schrödinger equation. We wrote the one-dimensional case, but the generalization to 3 dimensions would be kind of trivial. So this was the time-dependent Schrödinger equation we had. And now we said, okay, what if we are looking for the possible energy values? So we looked for a solution that has a definite energy. And then the wave function with a definite energy should satisfy this equation. Of course, this assumes that V is time independent. So, okay, nice. We have our equations, but what do we do with them? So you mean the particle in a box problem? The wave function? No. They don't have to oscillate. We will see some cases. Now, of course, we discussed the particle in a box example. In that example, we had obtained that the wave function, the second derivative of the wave function, has to be equal to minus k squared phi with the boundary condition that at x is equal to 0 and at x is equal to L, the wave function has to be 0. Because just outside the box, the wave function is 0. The wave function should be continuous. So just inside the box, it should still be 0. Because the position didn't change for the wave function to change significantly. Now, then we looked at the cases when k squared was positive. And we had found that the solutions was square root of 2 over L sine n pi over L x. This is what we had done on Monday. Now, we didn't look at the case, is it possible to have k squared negative? You see, I put this k squared, I define the energy to have this in this form. That is how I define the k squared, but I don't actually know E is positive. You see, energy contains the potential energy. Potential energy can be both positive or negative. So we will see many examples where the total energy will turn out to be negative. So what happens if k squared is less than 0? Well, let us just define some positive k squared. If this is the case, then the wave function, the second derivative of the wave function as a function of x, should be this kappa squared times phi. Well, the solutions, well, phi of x will be a times e to power kappa x plus b times e to power minus kappa x. This is the solution, the general solution of this differential equation. Then we have two boundary conditions. We know that phi of x is equal to 0, which is a plus b, should be 0. But this tells me that my general solution is actually, let me take a out, e to power kappa x minus e to power minus kappa x. But then I have the second boundary condition. Phi at x is equal to L. It should be 0. E to power kappa L minus e to power minus kappa L. But you see, kappa is we can define it to be a positive number. Kappa is a positive number. L is a positive number. This is a positive number. So this is a number larger than 1. Whereas this is a number less than 1. So that difference cannot be 0. If that cannot be 0, then A should be 0. Which tells us that there are no solutions with E less than 0. You see, in this problem, our boundary condition basically tells us that it should oscillate at least once. It is 0 here, it is 0 somewhere else. In this problem. We will see other cases whether such a solutions will be possible. Yes?
How is E less than 0? How is E less than 0?
E is not less than 0. E to the power minus KL is less than 0. If the E is some number like 2, 2 to the power, let's say, minus 1 is 1 over, oh, sorry, not less than 0, 1. Sorry, you're right. These are 1. This is definitely larger than 1. This is definitely less than 1. So the difference can never be 0. Okay, so any questions on what we had done on Monday? Well, if you ask me how we drive these Schrödinger's equations, we don't. Just like we don't drive the f is equal to m times a. So the claim is that, okay, this is the equation that describes nature. So we should test it by comparing with experiments. Now, any questions?
Az önce demiştik ya, enerji sıfırdan küçük olduğu zaman bir solution bulamıyoruz diye. En azından dimensional bir solution bulabilir miyiz?
You see, we already have our constraints. Any solution that doesn't satisfy that is not a solution. In a sense, or if you like, we had already found an imaginary solution where kappa was imaginary. That is sines and cosines, the oscillating solutions. But that is for energy positive.
Constraintlerimiz değil mi? Bölgenin içinde olması.
Yes. It's definitely inside the box. The potentials are infinite outside the box. Well, in fact, we said that the potential outside is infinite. That automatically forced my particle to be inside the box. The probability outside should be 0. Otherwise, I cannot have finite energy solutions. If the potential outside is infinite, and if my particle can be outside, that just tells me that the total energy is infinite.
For a problem, if we find an imaginary solution.
What do you mean imaginary solution? The wave function can be imaginary. There is nothing against that.
Okay, so what does it mean?
You see, the wave function doesn't mean anything. The probabilities will be finite, will be real. There is nothing that prevents the solutions to be imaginary. But at the end of the day, it's not the wave function that we are measuring. We are measuring the position of objects or the momentum of objects or the energy of the objects. That's what we are measuring. They should be real. Now, let's say if you want to measure let's just imagine an experiment. What you can do is you can create a particle with a given momentum, and then you know the forces acting on it. Just think in terms of your mechanics course. you exert some force. It can be the gravitational force if you don't want to apply an external force. You give it some initial conditions, and then you just release it. Then it moves, and let's say you want to test its trajectory as a function of time. So you just wait for some time and measure its position after that time. But you don't do this experiment once. You do it many times, because you are trying to fix the initial conditions, but the initial conditions will not be exactly the same. There will be slight deviations in the initial conditions. So at the end of the day, what you will obtain, let's say you measure the position of your particle at a particular time, let's say, and then you just count how many times you find one position, how many times you find the other position. There will be some fluctuations, because at the end of the day, even if you do this experiment, let's say you throw a mass and see how long it takes, try to measure the range. Okay, you just send it once, send it twice. Well, the initial conditions will not be the same, so you have all that spread. Of course, in that case, you will not be using your hand, which is a very lousy launcher. You will construct some device that will hopefully throw it at very precisely at a given speed. Do you know the meaning of precise? Do you remember it? And it is this difference between precise and accurate. Okay, when I say it's precise, meaning that the speeds will be very close to each other. There will be experimental errors, definitely. And depending on which initial speeds you have, you will measure some of the particles after a time t. You will measure some of the particles at what you predict, most of them at the position what you predict. And then there will still be some measurements outside that region. But if your equipment is good enough, precise enough, if your setup is fine, you will see such a histogram. Now, what this histogram tells me that, let's say, there will be, I create my setup, I launch the masses, I measure the ranges or its position after a time t. The majority of them will be at this position. Let's say 1,000 of them will be at this position, but 100 of them will be slightly further out. 100 of them will be slightly closer to the initial point, and let's say 1 or 2 will be even more further out or closer. So these will be our experimental errors. And when you quote the experimental results, what you say is x is equal to x0 plus minus delta x. So you have the average value of the positions. X0 is sometimes, quite often, it's the average of the outcomes. Delta x will be how much it deviates. So how you define x0? X0 is just the nth outcome, the outcome of ith outcome. You just sum them up. And you make n measurements, you just divide by n. This is the average value. And then you have let's say delta x squared will be just the again, 1 to n. The deviation from the average squared, and then you again divide by 1 over n. This is how we would define, even in classical physics, the average, the deviation. Well, let's look at this one. And again, for simplicity, let me just assume that xi just gave me 5 different values. Let me call those values y0, y1, y2, y minus 1, y minus 2. I can rewrite this as number of xi is equal to y0 multiplied with multiplied with y0 divided by n. So among these terms, there are many of these xi's is equal to y0. So I just sum them up. It's just y0 times their number. And there is this 1 over n. Plus number of times when xi gave me y1 divided by n multiplied with y1, etc. Now that we can imagine this one. We are doing this experiment. What is this number? Well, this is the number of one outcome over all the outcomes. But that's nothing but the definition of probability. Probability of xi is equal to y0 times y0 plus probability of xi is equal to y1 multiplied with y1 plus etc. Well, this is easy to generalize. Let me write it in this way. Probability of xi multiplied with xi over all, this time the summation is over all possible outcomes. Well, xi need not, if it is a position, for example, it will not take discrete values. It will be a continuous variable. So I can just convert that into an integral using the probability density. So x0, or sometimes it is denoted by this notation, sometimes with an overbar, is nothing but the integral of the probability density multiplied by x over all possible values of x. This is the average of x. But this definition is now something we can also use in quantum physics because we already know the probabilities. So the quantum mechanical average, let's say x average, will be this one. Let me also put the time dependence, which is usually written in this form. So soon it will be clear why we separate the conjugate and the wave function like this. This is the average. And this is, in fact, what you should compare with the experiment. Of course, this doesn't tell us anything about the individual experiment. But if you just do many experiments, repeat your measurements over and over again so that even classically you can determine the average and the errors in your measurements, if you do many measurements, the outcomes will be given by this quantum mechanical average. You see, wave function itself doesn't have any physical significance. Let me put it this way. We cannot measure it. Nothing. The physically measurable thing will be the absolute square of the wave function. Individually, they will not have any meaning. Next year, after you take classical mechanics 2, and if you still haven't seen the relation between the classical mechanics and quantum mechanics, and the wave function in quantum mechanics, then come and ask me that question again. There is an interesting connection between classical physics and the wave function. But those things you will learn next in the classical physics too. Not the first semester, but the second one. Okay, now let's see, what about the momentum? Well, we had already mentioned one thing about the momentum before. You see, we said that, okay, if we have the wave function, I can write it as a Fourier transform of e to power I p over h bar of x. Let me use phi of p dp over 2 pi. And then first let's see what is the psi of x. Sorry. Let us try to see what is phi of p squared dp. Well, before I had already claimed that this was the probability density for momentum. But for that to be a probability density, this integral should give 1. Otherwise, it won't be a probability density. I should divide it or multiply it by a suitable constant to make sure that this is actually 1. Well, let's see. What is phi of p? Have you seen Fourier series, Fourier integrals? Fourier integrals? No. Okay, so do you know how to obtain this phi of p from this integral? Okay, forget it. Okay, so forget it then. It's not so important. I'm sorry. Okay, so this is the position. Now let's try to do something with momentum. Now, when we were discussing the Schrödinger's equations on Monday, we said that, okay, let's look at a wave function. Let's assume a wave function which had this form, I kx minus omega t, and then we wrote this as e to power I over h bar px minus et. And then we said, okay, if the wave function is like this, and we want to somehow insert this wave function into our energy equation, we took its derivative with respect to x. We said that, okay, we have our wave function. So if I take the derivative of my wave function with respect to x, it will be I over h bar p times psi, or h bar over I times the derivative with respect to x of psi is equal to p of psi. Now this is nice, which basically tells me that instead of the momentum, I can just take the derivative. So we define the average of momentum to be dx from minus infinity to infinity, psi star of x of t times h bar over I del over del x of psi of x of t. This is how we define the average of momentum. Well, once you learn Fourier series, Fourier theorem, Fourier integrals, you can actually prove that this is so. But for the time being, let me just leave it here. 4:30? No, you should be learning it this semester at most. You will be definitely using it next year. You should be learning it in 2.9 or 2.09 or 2.10. Okay, so then you are learning it this summer. Okay, so your summer work.
Fourier transform daha şey, farklı.
Fourier integrals, Fourier transform, they are the same thing. Well, the difference between the series and integrals is Fourier series is for functions that are periodic. Fourier integrals is for functions that are not periodic. Okay, so now we know how to calculate the average momentum. Now, in fact, in general, so what we will do is, you see, on one hand we have classical physics. And on the other hand we have the quantum physics. We had already seen one case where in classical physics we have this concept of momentum. No, we started with the free particle. This is the free particle solution. And then, of course, we added the potential energy also later on. That was just a reminder of Monday's lecture. You see here what we have. On one hand, we have the classical concept momentum. But when it comes to the quantum mechanics, we cannot use the momentum. But what we use instead is this thing. What it does is it takes your wave function, does something on it, and gives you another wave function. Well, it, in a sense, operates on your wave function. This is called an operator. We have the P in classical physics. In quantum physics, we have the momentum operator. We will, most of the time, show the operators with a hat. And this we had defined as h bar over I, del over del x. This is the x component of the momentum. For the y component, you have the derivative with respect to y. For the z component, you have the derivative with respect to z. In classical physics, we had the energy. Now, in fact, we have a different operator. Let's say the energy operator is h bar I, h bar del over del t. Why? Let me just remind you what we had done over here. This operator over here, when I act on a wave function, it gives me the energy. That is why we call this the energy operator. Well, we also define in classical physics, you haven't yet seen it, but the Hamiltonian operator, Hamiltonian is defined as the kinetic energy plus the potential energy. Well, now we have the corresponding operator. Well, just to complete this prescription, let's say, in classical physics we have the position. Now we will also define a position operator. Now the position operator is kind of nice. If you have the position operator, multiply it with act on it to a function of position, it just gives you the position. If you take the momentum operator, act a function with the momentum, it might or might not give you the momentum, etc. Well, when I was defining it over here, my motivation was not that, well, in a sense, yes, in a sense, no. You see, since I'm talking about the wave function at a given point, well, I cannot talk about the momentum. It's not that I cannot measure it. I just cannot. It just doesn't exist if I'm talking about position. So instead of the momentum, I can still use the momentum operator. Now the Schrödinger equation is nothing but the energy operator acting on the wave function should be equal to the Hamiltonian operator acting on the wave function. This is the Schrödinger's equation. Now, if you want to calculate the expectation value of any operator, let's say of position and momentum, this is just the integral over all space. Let's just write down the one-dimensional example. Psi wave function conjugate, xt, you replace them with the operators, psi of xt. This is valid for any operator that you like. A classical concept, if you want to predict its average value, find the wave function, replace that classical quantities by the operators, put it inside the conjugate and the wave function itself, integrate, that gives you the average. Anything. For example, G can be just X, as we had seen before, or G can be just P. These are the two cases that we had written before. Or, for example, G can be this one, which is do you remember this quantity? LZ. The angular momentum. Of course, if you want to define angular momentum, you have to go beyond one dimension, at least 2 dimensions. You have to have the x and the y components. But the idea is, whatever you have in classical physics, just replace them with the corresponding operators. Well, everything in classical physics is expressed in terms of momentum and position. So whatever quantity you have in classical physics, replace them with their corresponding operators, and that is how you can calculate the expectation values. And in fact, if you just do that, the same thing for the Hamiltonian, Hamiltonian is equal to energy, well, this is nothing but your Schrödinger's equation. Now, I repeat, this is just a recipe which there is no derivation of this recipe, but this recipe works. That is what we know. Okay, let's give a 10-minute break and see you after 10 minutes.